So let's get started with session number 3 of our 4-part series on SPC. Again, these sessions are being recorded. If you haven't seen the first 2 sessions, we'll make them available once we're done. But I wanted to introduce Jim Bossert, who is going to be the presenter of this material. And I've introduced him previously, so I'm going to skip over some of that and jump to some new stuff. Jim was named Quality Magazine's Quality Professional of the Year in 2018. Jim has authored the Supplier Management Handbook and the Supplier Certification, among other books. He is an ASQ Fellow. He received the Distinguished Service Medal from ASQ in 2012. Dr. Bossert received his Master Black Belt certification from General Electric. He is the past editor of the Six Sigma Forum magazine. Jim received his PhD from Indiana State University in Technology Management, specializing in quality systems. He received his master's in applied math and statistics from Rochester Institute of Technology. He is an ASQ certified quality engineer, quality auditor, Six Sigma Black Belt, Six Sigma Master Black Belt, and certified quality manager, operational excellence. He also has his CHPQ certification and is a reviewer for the Journal for Healthcare Quality. So he's a very distinguished gentleman in the ASQ Society and in his work. And with that, Jim, you're on tap.
Thank you, Stephen. Greatly appreciated. So today we're going to spend time talking about the next level of control charts that were developed. And these are charts for discrete data. Because one of the things that happened is that after Walter Schuhart had developed the X-bar and R chart, they started saying, well, gee, we don't always measure stuff. Sometimes we just pass or fail it. Or we have destructive testing, so we can't really take a lot of samples and look at them. So we have to do something. So what they started to do, what he did and others like W. Edwards Deming, was to say, okay, are there types of control charts that could replace inspection? Because inspection was the thing that most people did to validate quality back in the 1920s. So they started to say, what can we do to reduce inspection? So part of it was to develop a thing called with discrete control charts. You had to look and say, are you looking at a defect? So a particular thing that's wrong? Or are you looking to say that the material or part is defective? A defect is something that is incorrect but does not affect the function. Okay, we can think of refrigerators that have cosmetic defects and allows us to buy it for $100 less than the unblemished part. But if it's defective, it prevents the product from performing. Okay, so in some of the examples, you're going to see examples of circuit boards where we look at defectives because the circuit board will not work if a certain part or an element of it isn't working correctly. So we're going to talk about what those are and how they work. Effective control charts, and these are the ones I like starting with because these are the things that most of the time people are familiar with. It's basically a pass or fail decision. Okay, so we look at how many failures we have over doing it from a sampling plan and doing sampling inspection. We'll look at these type of things. So the control chart will basically say, is it something that's good? Is it good or is it bad? And make a decision on it. There's two types of charts, a P chart and an NP chart. P charts traditionally look at percentages. NP charts looks at the counts. Okay. And the assumptions we make here are pretty standard. The probability of a defect is constant within the sample. So if we're sampling 30 items, we're looking at the same level of defect or probability of defect occurring. It's either pass or fail, success or failure, and we're going to have so many independent trials. Okay, and so when we do it, and I say independent because what happens in one trial does not influence the outcome of any other trials we do. And so it's very important to think about that and to work from it. So simple one is cell phone manufacturer was testing circuit boards before they're placed in the product, and they have a diode that's green if then the board passed, but if the diode was red, they put it aside for rework. So the company used a P chart to track the failure rate. Now, interesting story with this is that while we use diodes and use red and green a lot, I was working with a supplier who was testing circuit boards, and as I was walking down the line, I saw a red diode light up, and the operator passed it. And so I stopped and asked why. And the person in the factory explained that as long as the light came on, they passed it. Turns out that the person was colorblind and couldn't tell the difference between red and green. And they did not think of that when they were developing it as the criteria. So one of the things I had to do is actually develop criteria for testing for colorblindness for certain jobs at that point in time. So, sometimes you find what I call unintended consequences when you put something in place. And this is just one of those examples. So it made me very sensitive to color blindness. And it's amazing since I've become more sensitive to it, how many people I've found out are colorblind somehow. and it made me more aware when I do graphics, how I should do them. It didn't stop me from putting red and green lines on here, though. As you see on the P chart, we have a process here. Now, this is an interesting process because notice we're looking at it over 30 days. And as we start looking at that, we start going, I had an awful lot of failures early on. And then it goes down and seems to stabilize for the most part, and then it gets really, really low. Now, the key here, and one of the things I'm going to talk a little bit more as we go on, when we start talking about looking for what's happening in the process. When I see something like this going on, I'm looking and saying, okay, what happened early on? Was there something causing these circuit boards to be more defective? Was it, what was happening with it? And sometimes it might be the batch that came in. Sometimes it might be something else, but you got to look at it and start thinking. So, when I see something like this, when I see the data from the 1st to the 15th, and then from the 15th to the 30th, there definitely is something going on. And so I'm going to look to see what might be different. And later on today, I'm going to start talking about when I see something, what should I look for? Okay, so this is just, a good example. Here's another one where a company was receiving a large number of complaints on their invoices being incorrect. Okay, so the quality department did an audit of the invoices over a period of 30 days, and they would pull 10 invoices and see how many had an error, which we'll call a defect. And they used an NP chart to track that. And this is fairly common with a lot of places that are not, I'll say, outside of manufacturing areas, where they're looking at the clerical group or the office group, behind the scenes groups, to see, do they have something that's causing an error? And in this case, when you see, they started with, there were 4 errors on one set of 10. They found 4, and then they went down to 2, and you can see, again, they see a decrease. Now, in this case, people became more aware that errors were being looked at. And so as a result, they were a little bit more careful in putting the invoices together. And so as a result, you started seeing more with only one or two in it, as you can see here. And again, sometimes when people realize people are looking at things and they start paying more attention to it. So this is not an uncommon thing to see when you start looking at particular problems within a factory or within a back office operation. And, it kind of makes you think real quick in terms of what's going on, because if you're getting complaints on errors, there's a risk you might lose a customer. Defect control charts are basically charts that are based on a Poisson distribution. Okay. And there's two types of charts here. One is a C chart and one is a U chart. C charts looks at counts. U charts look at defects per unit. And the assumptions here are very simple. First of all, each defect is a discrete event. It's a defect and that's it. Okay. They can occur in a given area or region. And I think that's an important aspect, because when we start thinking about that, we need to think about, what the impact is. The defects are independent. So basically what we're saying here is that if I get a defect, I may not see another one, or I may get a different defect in another area. Think of cosmetic defects as an example. I know a friend of mine used to work in the paint shop at Ford, and he spent a lot of time talking about different types of defects they would get for painting cars and how they tried to circumvent those. Okay, but each one was considered different, and they would look at locations. And some of you may have seen examples where they've had charts which show where defects occur on a given piece of equipment or a given piece of machinery, and they use it what I call a dot diagram, where basically they're putting dots on it and to show it. And the intent is that to get an idea of where are the defects occurring, so you can work on it to fix it. Okay. And the other thing we think about is defects are a rare event. Okay. It could have a whole bunch of things, but what are causing the defects? We don't, and that's why they're Poisson distributed. It's something that just we don't anticipate defects to occur on a regular basis. Now, here's an example where a company I worked with was looking and saying, okay, they made quality improvements in the line, but they wanted to see it from the customer's perspective. So they basically pulled copiers off the shipping dock and set it up as a tech rep would do in an office. Now, these are big copiers. They're not little ones that we see like at our home offices. And so they would pull it and set it up, and they would see how many error codes came up during the process of making it. And they used a U chart, so it's a defects per unit. And if the improvement processes were working well, what they knew was that the defects per unit would go down. And so this is what the chart looks like. Kind of similar to the other one we saw, okay? But again, now we're looking at proportions, so it's a little bit different. And what you're seeing here is, the lower the number of codes that come up, the easier it is to make sure it gets up and running. And the guidelines for this particular company at the time was any copier should be set up and be able to be run within 1 hour of installation. And so they would look and see what kind of codes they were getting, so they make sure they have all the right equipment in to make sure they could make it work correctly. And again, it will do certain things and make it work well. Now, another example though for C charts is the legal department was changing disclosure documents. Okay. They wanted to make it easier for customers to read and understand. So they created some drafts and sent them to proofreaders to go through the document and see how many errors were in there. And they used the C chart to track it. So in this case, proofreaders were looking at documents and seeing where were errors. And they weren't looking just at spelling errors. They were looking at punctuation errors, grammar errors, and all that. And, I'm sure we all know and love reading legal documents because they're so exciting. But, I think we sometimes forget that somebody actually has to read them. And when proofreaders read something like this, they do it a little differently than what we do. We read basically from the start to beginning. Proofreaders read from the end and go to the start. So they're reading it backwards. And what they're doing is they're looking and saying, how many things do they find wrong, whether it's a grammar, whether it's spelling. And with spell checks, you don't find too many spellings except for certain words that just can be spelled differently, like there, T-H-E-I-R, and there, T-H-E-R-E. Okay, so you get a few words like that that sometimes will pop up. But if you see here, over a period of days, they saw how many errors they were seeing in a given legal document. And you can see that over a period of time, they averaged 4 errors per document, which is kind of interesting. How many times you got to fix something to make it right, but it's legal documents are different. So, but anyhow, they use the C chart. Okay, so in going through that, this is some of the things that we run through, we check and we validate. We say, Now, again, let's go back and think about it. Why were these charts developed? Well, the examples I gave you were all examples of things where either the product was, you could check it and you might be able to rework it. But there are some cases sometimes when what we're testing is once it's utilized, it can't be used a second time. Okay. So think about a case where you're making a thing like photographic film. And I know nowadays it doesn't work anymore, but people don't use film. But it used to be to test photographic film. The only way you could test it was to develop it. And once you develop it, you can't use it anymore. It's destructive testing. Now, when you have those type of tests, you have to be very, very careful because you can't use a lot of material. You got to use very little and try to make it so it works correctly. So the challenge we have is how do we make it so how do we sample and get a lot of things correct so that when we do the sampling, we make a good decision and say either we accept or reject it. Okay, and so destructive testing is one of the things that we have to be very careful about. And, we can see a lot of different examples of that. I mean, there's some things that are one use only and they never get used again. Military has a lot of those. Okay. So, if you happen to be in one of those situations where you're doing destructive testing, you want to keep sampling to a minimum and you can still use these charts. It's just you're going to have the risk you have is that you may have wider limits. So let's talk about causes. We have common cause variation and we have special cause. Common cause variation is the stuff we don't worry about because it's present. It's there. It's the inherent variation that happens. It's kind of like what we talked about in the first week where we talked about things happening like going to and from work or from classes. Sometimes it takes longer, sometimes it doesn't because of outstanding things that happen, but it's random and it's, generally it takes you, let's say 10 minutes to get somewhere. You just know it and you have it, but you don't worry if it's between 12 minutes and 8 minutes. You just know it's going to take that. There's nothing that's directly influencing whether or not it changes dramatically. Okay. And when common cause is present, we're very happy because our process is considered stable and predictable. And that's important to remember. That's why we like process behavior charts or control charts, whatever you want to call them, but they're because it tells us when a process is stable and so it's therefore predictable. The hardest part I have with people putting these charts into place is sometimes telling them if the process is between the lines, and it's usually when I start with something very simple. As long as the process is between the lines, don't mess with it. Don't touch it. Don't do anything. And it's hard because people want to inherently do something to try to make it better. Okay, so when we have common cause, we want it to just hands off. Special cause is usually caused by something that happened in the process. So we might see a large change, and I'll show an example of that in a minute and tell you a little about that. Or you might just have something that just all of a sudden you got a movement where it's a shift. Okay, so now it's moving, working at a higher level or a lower level. Okay, or you see a trend that's going down or up. Okay, when we observe an out of control point, we want to react to it and do something about it. Okay, so we want to further investigate to see the cause. Now, sometimes an out of control condition happens because you made an improvement and it actually is running better. In that case, you want to make sure you understand what happened, what changed, and try to lock it in so it stays that way, because now you're performing before. Okay, so we want to basically try to do that. So when special cause is present, it's unstable and it's unpredictable, and so therefore we want to know what can we do? How do we make it more predictable? That's our challenge. So let's talk about some of those out of control tests. When we first started, Schuhart, when he first made control charts, he only had one out of control test, and that was a point above or below the control limits. And basically, the probability of that point being out was 0.27%, very small. All right, so he wanted to make sure that he always had a very, very low rate of failure. So he wanted to make sure that the probability was always low. So he wanted to have different tests. Different tests were being developed because they started seeing different types of patterns. And so what they had to do, for example, is how did they get to decide what some of those tests are? Because we're going to talk about the different tests they have that Western Electric developed and some others. And basically, for any new tests that were out of control, it had to be at or below the threshold of 0.0027. So, for example, test number 5 that you're going to learn about in a minute says 2 out of 3 points are greater than 2 standard deviations above the center line. So, what's that mean? Well, if we take the risk, the alpha risk of 0.05, and we square it, we see that the answer is 0.0025, so it's less than 0.0027. So we're saying, okay, that is something that's important. So when they can develop the out of control test, they use the rare event standard to work from. Okay, so we see that each test that we're going to go to is statistically proven the same way, and they will build on that. Okay, and if you're using Minitab, for example, they have 8 tests for continuous data and 4 tests for attribute data. And actually, it's the same with JUMP, and it's the same with SPSS. So any statistical package have these built in already because they want to make sure that people are consistent in the way they do it. So what does out of control mean? Well, it means that basically something happened that's highly unlikely that it's occurred. So we need to investigate it. Okay, and it's, as I said, a rare event. So we need to look and we need to see what happened. And like I said, it could be a good thing that happened. You made an improvement and it really improved. So that's something that we have to take into account. There are certain pattern characteristics that we talk about here. Okay, so when we talk about the pattern characteristics, we talk about natural patterns and unnatural patterns. Most of the points in a natural pattern basically are randomly scattered around the center line. Okay, and you're going to see most are around the center line, and then they spread out and approach the control limits, but none of them exceed the control limits. So think of a normal distribution. With a normal distribution, what do we see? We see most of the lines in the center, where the mean and median are the same, and it spreads out. And the farther out we go, the fewer points we get. If it's an unnatural pattern, what we see is that the points aren't necessarily around the center line, but rather may be higher towards the limits on both sides. Okay. And so we see some things going on, which may clue us into something going on when it's outside of the center line. And that's what we may call a mixture pattern. I'll show you what that looks like in a minute. You could have something that is always around the control limits, nothing around the control limits, but hugging the center line. So it's very, very consistent. And that's a concept known as stratification. So we'll talk a little bit about that in a minute too. And then, we get it outside of the control limits, the points that go up, the oops type things. And that's what we call instability. So as we go through and all that, we'll look at these, at the different patterns. Okay. I'm going to use P charts in the examples for these, but it applies to all control charts. Now, in this case, we have instability, and we see a point that falls outside of the 3 sigma limits. Now, notice in this one, and this is one that came from Minitab, so it has the number that it's showing. It's got high fluctuation. And, this one shows an awful lot. Usually what's more likely for us to occur is when something is going on that it shows 1 point out, and then you have just a very stable process. Everything's in except 1 point. And you have for that time frame, with that difference to look in to see what's going on. So, we see different things that can occur. What you have in here is if I look and see at the pattern we have here, did we have different operators? So did I have operator 1, operator 2, or operator 3 doing it? Did we have something like a power surge that caused something to happen? And now companies like to say they don't have power surges, but yeah, they happen. Or did we have different materials introduced and they weren't thoroughly mixed? So they came in and all of a sudden it had a different change, whether it's in viscosity, it might be in the pH, it might be something else. So that those things occur. We've had a shift change. Okay, when new shifts come in, you may see a different level of operating because operators like to tweak the machine just to make sure it's working right. And when they do that, sometimes it causes a blip. Hardest thing for an operator, and I worked as one for a number of years, you want to tweak it to make sure it's looking, but when you put a control chart on, all of a sudden those tweaks become noticeable. And so you have to teach operators to keep their hands off. And that's hard. It is really hard to get them because they're so used to touching the machine and just turning it a little to see if they see a blip. But on a control chart, it causes all kinds of headaches. The other thing, though, sometimes you'll find, especially if it's something like a circuit board that has a number of different layers on it and different lines that you're running, some of them might be damaged at shipment. They might be damaged in inspection. It might be damaged in handling. And so you have damaged components that are taking place. And when that happens, this is going to cause some issues for you also. Now, this is the one of them that I've talked about. 2 or 3 successive points fall near the control limits or beyond. So in this case, got 2 points here that are circled that are basically close to the control limit, and they're going beyond. So it's known as instability. And you can see here, it creates kind of like what I call a mountainous look to it usually. And so your instability is bad. Now, what's interesting here is depending on what you're looking at, the part that's circled may actually be something that's more desirable. Because what you're doing is saying you got low level of defects. If I can find a way to replicate that, that's going to give me a better production run. And it's actually going to tell me how I can make things better and more consistent. And what you got to do here is it's pretty simple. You're looking for a change in materials or a change in settings. And, when I talk about changing materials, one of the things that you have here, and those of you who are thinking of becoming chemical engineers or working with chemicals, this is something you're going to find is that every time new materials are introduced, you've got to be aware of when it's coming in and make sure that they're pretty close to the same in terms of material conformity. Okay? Because sometimes you will find things that will upset it. Worked a lot in plastics. Plastic pellets, notorious for having different water content, which creates a whole problem when you're putting it into blow molding or a different blow cavity moldings, different types of cavities that you're using, injection molding. So you got to be very careful with the materials because sometimes it'll be thinner, sometimes it'll be thicker, and you have to change the pressure. So you have to look at things like that. So you look for change in material, change in settings. If I have 4 out of 5 successive points that fall in that are greater than 1 sigma, okay, which is what you see here that's circled. Now it's telling me I got to look at it and say, why is it settling up there? Is it going to go down or not? Now, in this case, it did go down, so I didn't get as worried about it. But the thing is, when I see 4 out of 5 successive points, that's greater than 1 standard deviation. And 1 standard deviation plus or minus is 67% of my data. So I'm looking for what's unusual, what's between the 67% and the 3 sigma line or the 2 sigma line, which is 97%. So what's greater than that? Is there something funky going on? Okay. Now this can happen a lot of times when a new operator comes in. And so when a new operator is basically coming into the line or learning how to use it, they may end up creating some problems just because they're looking at it differently, they're setting it differently. They may have tweaked the machine and set it up, and then somebody said, oh, you got to turn it back. Okay, so you got to see, you got to look. It could again be new materials. You're going to find materials come in here a lot, and it's something that you learn when developing equipment or developing processes, how to control the introduction of new materials to try to minimize the variation that goes on. But it is real. But the other thing that sometimes happens, you have a startup. I had a machine downtime, and now I'm starting up again. And so I have to make sure it's all set and ready to go. And I have to make sure there's certain things you do in a startup. And so you have to make sure the process is followed correctly and that things are taken care of. And before it settles in, you may want to scrap those initial parts because the startup problems may create more problems for you than not. So you have to carefully look for stuff like that. Next one, we got 8 points in a row on one side of the center line. So I find something that's running consistently high or consistently low, but it's above or below the center line. So I'm seeing it and I'm going, what is happening here? It could be a sign of a shift. It could be a sign of a number of things changing, but part of it is variation in the sample size. I may not be taking the same sample, or when I'm pulling the sample, it's not random. Maybe I'm pulling the first 5 pieces off the line or the first 6 pieces off the line instead of the first doing 5 interspersed across the whole within an hour. Okay. I might just I'm pulling some sample sizes, I'm pulling 5, but I got my coworker is pulling 6 or 7. They're still looking at them and they're saying, okay, I've got to do something with it, but it's a pass or fail test. So therefore, they just pull them and see. Some people like to do it that if they get a failure, they pull another sample right away. just to make sure it's either a failure or not. And that's, if you think about it, that goes against sampling theory. You're saying if you pull a sample, you don't pull a second one right away, but there's a lot of old school operators who will do it that way. Okay. It might be the tweaking the process. They think they can do it just a little bit better than somebody else. So they're going to go and I'm going to adjust this pressure, or I'm going to do this because I think we can do it better. Generally speaking, we're trying not to tweak the process. I'm trying not to have them do stuff like that unless I'm doing a design to experiment, and then I'm telling them how much to tweak it. But that's different because then I'm trying to define an operating window. So sometimes people will touch it and they'll just try to tweak it a little bit. Sometimes it'll be different batches. It's kind of like different raw materials coming in, but you may have a different batch. Some of you that that have done painting or maybe weaving or anything with yarn, different batches may not have the exact same color. They may be just a little bit different. So as a result, it creates a problem for you. But, the other thing that comes out is this last one here. Everybody likes to go to automatic controls. These automatic controls are great. The machine regulates it. Well, the machine can create some real problems for you. Because what happens with automatic controls is how they're set up. It can create a situation where you get a sawtooth pattern. We'll talk about that in a few minutes. Or you get something like the one we had before where it just keeps changing. So you have to think about what the automatic controls are doing and how it affects you. We have something like this, 15 or more consecutive points that hug the center line. Okay, and that's why I call this stratification. This is, I call it, the other thing I call is artificial consistency. It's really good for some reason when normally the process doesn't show that kind of variation. So what is going on here where we're seeing very little change going on? Okay. Part of that might be non-random sampling, as we talked about before. Sometimes we're taking samples from two different processes. I may have two machines that are running the same process. And what I'm doing is I'm pulling one from one and one from the other. I don't know which machine it came from. All I know is I'm looking at a product and inspecting it after the fact. And I don't know which machine it came from. So I might see a sawtooth pattern because one is running at one level, one is running another. Okay, so you just don't know. I might have just two separate associates again doing the same thing. So they're being very consistent, but each one's running at a different level because the machines are different. A mixture. When I have a mixture pattern, okay, I've got 8 consecutive points on both sides of the center line, but they're at the extremes. They're running high and low. A lot of times for me, when I see this, I immediately look for, do you have two separate equipment, separate operators? Because this is exactly what I'm talking about here. I've got two equipments. I might be adjusting. Okay. People say, oh, I'm too high, so I'm going to adjust it. And they turn it down too low and it goes too low. It might again be that automatic control system that's set up by the machine because it's not working properly. Okay. It might be just in the way it's being measured. Are we measuring it the same way consistently, or am I trying two different things? Am I doing one with calipers, digital calipers, and maybe the other with dial calipers? Will I see a difference? Sure will. I could have mixed materials, and that will happen. Sometimes people just get tired. I can say, when I was an operator and I was working multiple shifts, the risk of making an error or having something like this occur was higher on the midnight shift than any other. And it's not because you try to set it up and make machine run. Sometimes, you get tired looking at a machine, and quite frankly, your eyes kind of doze off, and all of a sudden you realize, oops, I got to make an adjustment. Sometimes human error comes in, though, when you plot the wrong data. Okay. Now, I know people like saying, oh, we're going to use automatic plotting because that's better and all that. But you got to have the sensors to do it, and you got to make sure the sensors are calibrated. Okay, so these are things, again, when you see a mixture, there's a lot of stuff to look for. I might see a trend. Things are going down and getting better. And when I see a trend, I need to start thinking about what do I do? How do I control it? What are things I need to do? Now, if I'm trying to reduce something, if I'm trying to reduce defects, this might be the kind of trend I want to see because of an improvement project I put in. If it is, then what did I do right? Okay, so you have to start looking at it. Do you have a new procedure that you put in place? Did you have better skill levels? So as people got better, as you learned how to use the process better, you know, put a new thing in place, you got a learning curve. You got people who learn. As they get better, defects will decrease. Okay. I might have put in some statistical process control in some other areas. And because I put them in other areas, now it's better. Now they've actually done things and doing it. And it might just be, hey, the supervisor's walking around better. So as a result, I'm paying more attention to what's going on because I don't want to get in trouble. Cycles. Cycles occur, and these are things that, again, we have to look at and make sure that everything is going on. But it's a good example of a cycle. Now, this one's kind of interesting because if you notice it, we've got the cycle going on, and it's all on the low side. We don't have anything really cycling on the high side, which again, kind of when you start looking at this, saying, what is happening with this? This is where we can get things like seasonal effects. When I was working in one area that had a product that was very sensitive to humidity, it wreaked havoc with us because the more humidity we had, the more difficulty we had in getting a consistent product. And so things like fall and spring, we were constantly working on the process because operators had to work extra hard for this particular chemical process because humidity played an effect. And the company was not willing to to basically control the humidity within the facility. They felt they should be able to do it with the process. And so as a result, we hated fall and spring. Wintertime, summertime, no problem. But during fall and spring where humidity and temperatures changed, it drove us crazy. Could be a result of fatigue. People get tired, and so you see cycles of doing that. Might be job rotation. Yeah, what I mean here is that people are switching off. So every 2 hours, I'm switching an operator. I'm switching people in to get a fresh set of eyes, a fresh look, but I could see cycles as a result. So I want to see how long those cycles are going on. What's the impact of doing that and how it works. Extreme outliers. Now, in this case, this one doesn't look as extreme because it's not outside of the limits. But if it was outside of the limits, and I did have a situation where this occurred, I want to understand what's driving it. This type of thing is called a freak. That is the technical term. And when I see a freak, I need to try to understand what caused it. In the case where I found this, where it was happening, it happened every month. So if I spread this out over a month period, I would see a freak occur when the mesh filter that we were using broke. And so it was letting bigger particle sizes get through than should normally be allowed. Okay, so we would see a freak. And it turns out, we could go and see this. And you had to look at it over a long period of time before you could find it. These are the hardest things to find. But when you do, it's kind of cool because when you fix it, everybody thinks you're a miracle worker. Okay? It could be plotting, it could be measurement, but quite frankly, I found it was usually something in the machine. And in this case, it was the filter we had. It's only supposed to let a certain size through. And after a while, it gets clogged up, and all of a sudden, the filter breaks. And when the filter breaks, you get a freak. Okay, so you have to look at that. sudden shifts. When I see something like this and it's an improvement project going on, I will leap for joy because a shift tells me that it's doing what it's supposed to do. And that's the kind of thing that you want to see. So a lot of times when I'm looking at process improvements, I try to identify where I might see a shift when something new is introduced and actually do it. And a lot of control charts nowadays allow you to put in when you think that a change took place so that you can actually keep track of this so you can identify, did you see a change and that you have a new level of operating. And again, some of this is very simple. It could be new equipment, it could be new materials, but it could be what? I made an improvement and it worked. Sometimes though, you'll find sometimes they change the requirements and they actually will let more stuff through. So, occasionally you'll see that type of thing occurring. Okay, so again, I'm just talking about pattern recognition here. What's a mixture look like? Oh, do you see the extreme swings that hug the outside control limits and not the center line? Okay, so that's telling me I've got over adjustments. The cycle, again, what's the cycle look like? How that pattern look? Shifts, in this case, a shift or a trend. Very similar sometimes, but what's happening with them? Okay. Now the Western Electric rules are the things that I told you they mention in Minitab and in all the packages. These are the rules that they say. So if they say rule number 1, you get 1 point. That's beyond the control limit, and that's basically what they're identifying. It's your freak. Okay. Number 2 is always 9 points in a row on the same side of the center line. Okay, so you may have a shift, it's something going on, but you need to look for that and see what's happening. Number 3 is the 6 points that are descending or increasing, which talk about trending. 4 is an interesting one because that's 14 points that are alternating up and down. Okay, and so this one, because it's alternating, this is where I usually look to see if I have 2 separate operators doing the same thing or 2 machines doing the same thing, and I'm just pulling stuff from both lines, and I just happen to be pulling one from one line, one from the other all the time, back and forth. Okay. 5, I've already talked about, 2 points out of 3 in a row above the 1 sigma limit. Okay. 6 is 4 out of 5 points, which again identify shift kinds. If I have the stratification or the artificial consistency, it's 15 points in a row within the first zone, which is in plus or minus 1 standard deviation. Okay. And then I have 8 points in a row on both sides of the center line, but none close to the mean. Okay, so those are the different points you look at. Are there any questions? Heard a lot of stuff today, so I recognize there may be some questions that people might want to have.
So we'll give you a minute or 2 if you want to type in some questions in the chat area. And then we can read those off.
Okay.
Maybe you could remind us of what the topic's going to be for next week while we give them some time.
Okay. Yeah, actually, it's in 2 weeks. It's not next week.
Yes, I'm sorry, 2 weeks.
Yeah. In a couple weeks, which will be the day after Halloween, we're going to be talking about process capability. How do we define capability? How do we measure it? And so what I'm going to do is I'm going to show you processes that are in control and what that capability looks like. And then I'm going to also show you some processes that aren't in control. They're unstable. And so therefore, we're going to see what the differences are and how the capability looks for that. So you get an idea of what an unstable process is and if you did a capability estimate, we'll talk about some of the different capability estimates that you can look at and how it works. So we're going to talk about CPK and PPK. Okay. And just see how they vary and what kind of things they do. So, and why stability is so important.
That sounds great. It looks like we don't have any questions right now. If you think of some in the meantime, you can bring them to your next session and we can discuss them then.
Sure.
Thanks so much,
Glad
Jim.
to. Thank you. Take care,
Bye.
everybody.